I had a Lebanese student once, and she said the thing about Catholic students is that they complain to the parents right away if you do anything at school, and they give you a whack. So you get a whack, you go home, each parent gives you another whack for what you did. So it's very similar. A very similar structure. Could we, like I mentioned, have an exam next Monday? I was wondering if you want to push it to Wednesday. I kind of like having our quizzes and things on Wednesdays rather than Mondays, but I didn't know how it is. I know many of you work, and if you're teaching 5 classes and then coming here after some kind of activity, you might feel so worn out on a Wednesday.
Yeah.
What, do you want to keep it Monday?
Yeah.
Okay.
I'd rather take an exam in this room, though.
That's the thing. The other room. I didn't like the other room. And I also feel like the other reason I wanted it on Wednesday was I feel like there's questions that people have and they ask me over the weekend and I think, wow, I wish I could address all to the entire class what they're asking, and I don't get a chance to do that because I'm spinning out an exam or quiz Monday.
Shall we have a show of hands?
Yeah, let's do that. How many opt for an exam quiz from now on Wednesdays? All right. Maybe we'll run a couple laps around University Hall before we, just to get the blood going. Okay, so I explained the breakdown already. Computational questions like finding subgroups. I'm going to show you some today from today's lecture. And then true-false questions. You're going to see some today. One proof you haven't seen before, and then one proof you have seen before that's with the solution. That's from the homework. So I talked about this already. Okay, so many of you remember the definition of cyclic groups from cyclic subgroups from undergraduate, but a cyclic subgroup generated by a element in G. The notation is this little symbol around the A, the little wings. If A is in G and we define H to be all the powers of A, then H is called the cyclic subgroup generated by A. A group then can be, if the whole group can be expressed as something generated by A, it's called, the whole group is called a cyclic group. And this is a common idea. Fraley actually talks about it in a little bit of detail in the book, but you've seen this before in other courses. In linear algebra, which many of you had last semester, at 8 o'clock at night. But we had it worse because we went till 11. Yeah, it's cruel. It was cruel. In linear algebra, you talk about subspaces. Those are actually vector spaces generated by a set of vectors. So the set of vectors by itself doesn't form a vector space, but you keep adding ingredients to it until you generate the entire space. So that's what you're doing here. You're taking this element A, and you keep adding ingredients to it until you get that subgroup with that with the powers. That includes all the powers. So for example, if G is Z6, G is 0, 1, 2, 3, 4, 5. That's what Z6 is with addition. Let's take A equals 2 and see what the cyclic subgroup generated by this 2 looks like. Well, A squared in this case would be A plus A, which is 2 plus 2, and that's 4. A cubed is A plus A plus A, but you're modding by 6, so when you add 2 plus 2 plus 2, you get 6, which is 0. A to the 4th is 4 A's, which is 8, but then you're modding by 6, so you get 2. And we're back to where we started. So the cyclic subgroup generated by 2 is really 0, 2, and 4. We don't get anything else other than that. By the way, is G itself a cyclic group? What generates all of G? 1. That was my next question. Is it the generator unique? The answer is no, right? You can find 2 generators in this example. So there's a nice true-false question. Let's see if you can make up true-false questions. Most of your teachers in here, so you like inventing little things that bother other people, right? Inventing little problems to bother other people, but little people. So this is an example of a group that's cyclic that has a subgroup that's also cyclic and isn't the whole group. So you could ask true, false. Because the group is cyclic doesn't mean that all its cyclic subgroups have to generate the whole group. Is that the only one that you get? Here you get a proper one. Z with plus, standard example. 1 generates Z because any integer n can be expressed as 1 to the n. For example, 3 is 1 plus 1 plus 1, and negative 3 is 1 to the negative 1, or negative 3. You can also here find some interesting subgroups that are cyclic. For example, the subgroup that's generated by adding 2's over and over would give you what? The evens. And that we already know is a subgroup. So there's an example of a cyclic subgroup.
What is, I don't get it. If it's an infinite cyclic group and the generator is 1, and in the second example minus 3 is equals minus 1 plus minus 1 plus minus 1, so you need to have 2 generators to be able to generate the whole group, or?
No, you don't need to have. You only have one. Right, you only have one
So
generator.
what is the generator then of the Z?
1.
How does it come out and start?
Because it's 1 to the n, where n is an integer. So it could be negative. The inverse has to be in there.
1 to the N.
Right.
Okay.
Got it?
Yeah, thank you.
In fact, a subgroup of a cyclic group is always going to be cyclic. Question, Sean?
On the last page, why was the group 2 a cyclic subgroup, not just a subgroup?
Because if you add power 2 plus 2 plus 2 plus 2, you get all the evens, right? And we already know that the evens form a subgroup. So all powers of 2 give you.
But when does it ever cycle back to the
You also have 2 to the negative 1, 2 to the negative, right? Just like Jeff was asking earlier,
Okay.
right? So, but I knew that any example I make where I knew the original space, the original group was cyclic, I would get a cyclic subgroup because there's a theorem on page 61 that guarantees that. So this is important because it tells you something about the ZNs, and this is why many books start out with ZN and they talk about ZN quite a bit because they make some interesting examples right away. They are an example of cyclic groups. And some of you in here used Hungerford, where they start with rings first, and they still do a whole session on ZN at the beginning and give you some number theory so you get those examples. So every subgroup of Zn can be represented as a cyclic subgroup. That's good proof fodder, as you already knew, because I think some of you were trying to use that earlier. So if you have to prove anything about Zn or subgroups of Zn, you can now use these theorems to say something about what that subgroup must look like. Okay, so in Fraley, there's one really weird thing that he does. He defines isomorphisms before he defines groups, which is a little weird because the whole idea of a group isomorphism is to preserve the binary action on the group and to preserve the group properties. So the two groups are said to be isomorphic if there's a function phi that goes from G to G prime, such that one, that function is 1 to 1. Second, that it's onto. These two paired together are called a bijection. And third, it preserves the binary action on the group. So acting in the group G, pairing things in the group G, is the same thing as pairing things in the group G prime. So really, when we say we have an isomorphism, it's like you take two seemingly different looking groups and you've now come up with a dictionary that tells you, codes for you everything in the second group to the first. Or like I like to tell my kids, there may be a planet out there that's exactly like yours, and there might be an Anjali out there that's a perfect match for this Anjali over here. So for every that's the example I give them. So they start looking out into space, like, is there really another me out there somewhere? So it's the same idea. You have two planets, and for every person on the other planet, there's a corresponding person on this planet. And it's 1 to 1. There's as many people on that planet as there are on this planet, and it's onto. Everybody's covered. So it's a code book. The third property really is pairing. So that's the idea of if two people get married on planet Earth, then two people, also the same two partners, will get married on planet Earth prime. So that's what it is. The pairing is exactly identical on both planets. So we have a nice theorem here that if G is a cyclic group with generator A, and if the order of G is infinite, then G is isomorphic to Z and with the plus. So that means all cyclic infinite groups are just really Z. The second one is if it's a finite order N, then G is isomorphic to Zn. And that's addition mod N. They have a little subscript N in your book to indicate it's addition mod N. So that means if you have a finite cyclic group, it's the same thing as being Zn. So you've seen a big theorem like that in linear algebra recently, where you had some kind of pairing of things. And that is the theorem, I don't know what you would, I know which book you used, but I don't know what they called it, where you looked at linear transformations going from Rn to Rm, and the theorem that is the code book tells you that those linear transformations are just n by m matrices. So instead of working, that's why, so the way that book builds things up, in that book, because you're in graduate school, it starts out with linear transformations, and you do all this stuff with linear transformations. I see the book in my mind, I just can't remember what it was called. And then it has this big theorem that it's got this relationship to matrices. But in undergrad linear algebra, what do? You spend the whole time on what? You blocked it out? Undergrad linear algebra? Matrices, right? You spend that entire time talking about matrices, row-reducing matrices, squaring matrices, multiplying matrices, and looking at all kinds of things with structures of matrices. Why? Because all linear transformations are really matrices. So if you know how to manipulate a matrix, then you know how to manipulate a linear transformation. And then now you grew up, and you're in graduate linear algebra, and you went to the big thing, the actual linear transformations. And so a couple examples, and I'll show you how I plan to do this on Monday's exam, and now it's Wednesdays. R with plus is not cyclic. Can you see that? Why wouldn't it be cyclic? Why can't you have 1 generate R? Huh?
Rationals.
Right, you miss all the rationals. There's no element, in fact, that you could repeatedly add that gives you all of R back. You'll now, if you take pi is always the thing that doesn't work out, right? Take pi, but you can't add multiples of pi to each other. You're not going to get all of the reals because you'll miss 1. 1 won't be in there, so you have a problem. Is it true that if G is finite, then G has to be cyclic? That was, I think, a misconception on the last quiz that we had, where some of you were saying, because G is finite, I can write it in this way. Is that true? Can you think of an example where that, you guys don't do this, I'm really tired, so if you guys are like this too, it's going to make me worse. Be awake and alert, huh?
Klein Group?
The Klein Group is a perfect example. Because, recall, I had you already actually take that Klein Group and find all the inverses of the elements. Do you remember what happened when you looked for the inverses, A, B, and C? They were all the same, right? So A inverse was A, and B inverse was B, and C inverse was C, or vice versa. You could say A squared is E, B squared is E, and C squared. So there is no cyclic, it's not a cyclic group, right? Because if you try to make powers, you just get E and the A, and that's it. Nothing else is in there. E and the B, and nothing else is in there. So that's cyclic subgroups, but the whole group itself is not cyclic. So just because it's finite doesn't mean it's cyclic. That's what you found. Make sense? So this explanation has to be there when you are talking about a true-false question, and you're saying, you can't just say, oh, the 4 Klein group, and that's it. I'm asking what you know because I want to make sure you know it, not for in this class, but for a comprehensive exam, or when you are in someone else's class, or if you decide to go get your doctorate. So it's what happens after here that matters. So I thought I'd just take 2 infinite groups and show that they actually are isomorphic to each other. So what do I have to show if I have to show two groups are isomorphic to each other?
I can step over.
That's fine. I must show that there exists an isomorphism. So I actually have to produce it. Here's my isomorphism. I have to show, once I come up with a candidate, whenever there's a there exists proof, you have usually a candidate, and then you show your candidate works. So once I have a candidate, I have to show that candidate is one-to-one, that it's onto, and that it preserves the binary operation. Those are the three things I have to show. So what's my candidate for phi? Well, it's the way I would imagine you would get an even number. Take the original integer a, and then just multiply it by 2, and you'll get an even number. That's my candidate. So the input of the things are things from Z. The output are things in E, the even numbers. So now I'm going to check that my candidate actually satisfies the requirements. So here's my proof that phi is one-to-one. How do you do that? You first assume that the y values from high school algebra are equal to each other, high school commutative algebra. I have to show that x equals y. So if phi x is equal to phi y for x and y and z, then 2x is 2y by definition of phi. Now here you have to be careful because you feel like canceling out those 2's, but you're working on the world of integers, so you're not allowed to divide out by 2's. But z is embedded in q, and there you do have a multiplicative inverse on q with 0 tossed out, and in there I may cancel the 2 from both sides. So if I embed z in q, I can do that. I can cancel it out of both sides, and I'm done. X is equal to y. Is it onto? How do you show something's onto? Well, the way you show something's onto is you start with the other planet, Earth prime, and you grab a random person in Earth prime, and you show that that random person has another one right here on planet Earth. So you grab Anjali from Earth prime and show that there's a corresponding Anjali over here on Earth. So let's try that. Take a z from the evens, and I need to show there's a u in the integers such that phi of u is equal to z. Easy? No pun intended. So if z is even, by definition, z can be expressed as z is equal to 2u because that's the definition of an even number. That gives me my input variable, that's the u, and phi of u is z, and I'm done. It's onto. Got that. So is it true that it preserves the binary operation? Do you want me to back up? Do you want me to back up? Sorry. Just stop me or else I'll just... Goran, why are you tired? Why are you tired?
No, I'm just trying to connect it all together. It's been a while since I've
Kyle, why are you tired? Why are you tired? Are you tired? You look more tired than usual. David's tired, I can see. Are you tired, Ted?
4 in the morning. I drive my way to the airport.
All right, see, I know something's going on. Everybody seems like... If I started talking monotone, everybody would fall straight asleep. I can see it. So is this part true? So how do I show that? Well, I take two elements in Z and I pair them, and I hope that the pairing still holds. The pairing is plus, right? So if I add the two elements first and I apply phi, well, that's supposed to be 2 times 8. So we get that. Well, we can embed it in the ring and distribute that 2. And then that's equal to phi A plus phi B. So adding in the world of Z is the same as adding in the world of the evens. So that's true. You know, one of the things is I remember how I learned this the first time. And for me, learning this the first time, you guys didn't have this if you went to Montclair, but we actually had what's called a baby algebra class. So we had a sophomore level algebra class, which was meant to be, it was only for math education majors. And so I got to sit there and learn the basics. And in that class, I looked at these kind of problems as I'm supposed to do this, but I didn't fully understand what that thing was. When I really understood it is when I watched the documentary called The Proof, and he talks about what an isomorphism is in there. And I thought, wow, that's what this is. That's why they make a big deal out of it. And then I got it. And then I started seeing them all over the place. Oh, there's nice. That's why they talk about these things. How many of you took real analysis already? In real analysis, do you guys talk about isometrics? Isometric norms and isometries? So you also, what is real analysis about in one line? Real analysis is about taking limits, right? See, that's what it is. Algebra is about solving equations. So that's what it is. So in real analysis, you're talking about taking limits. So in real analysis, you want to not just preserve the two spaces or vector spaces or whatever you're looking at. You would like to preserve the concept of taking limits in one versus another. And at one point, I know in real analysis, you had something about the p-norms. And they talked about all the p-norms being equivalent. That means that if a limit converges in one p-norm, it converges in another p-norm. So if you have a sequence of real numbers, and they converge, or real in Rn, let's say, and they converge under the 3 norm, they also converge under the 2 norm. So convergence is the same no matter what you change with the norms. So whatever it is you want to prove, it's an iso. They call it an isometric norm. Okay, so here's some homework. Some of these are not, it looks like a lot, but it's not. Some of them are true, false, so you have to just think about the examples. If you can't come up with the example and you're stressed out, don't be. Just send me a text, send me an email. I know how to nudge. I know how to give you that little push and start thinking. You do have to deal with me asking you annoying questions like, have you thought of this? Or what would happen if this happens? Or I do another one, fill in the blank here. So you'll get some of those messages, but I promise you it will be probably less frustrating than sitting and staring.
Today will be included in the test?
Yes. Which is also on the first page of the exam, of this PowerPoint. It says exactly that.
What does it mean explain what, if not let it be explained by the number example?
Oh, you can't just say the 4 Klein group.
Explain,
Julie?
just explain what
You have to explain why you said the 4 Klein group. I think about this all the time about the, when you're asking